My name is Eric Bosman. I'm here to talk about Minemu. Minemu is an emulator for x86, designed a process-level emulator designed to um, protect binaries from memory corruption attacks. So traditional stack smashing um, smashing has become quite a bit more difficult in the recent years, luckily. So in normally you used to inject your own code in a program, and then through a buffer overflow overwrite a return pointer on the stack to point to your code instead of the code it would execute normally, and then it would execute your code and done. Luckily, some things have changed. So address space layered randomization has made it more difficult to find your own code inside the address space. And the NX bit on modern processors have allowed operating systems to separate data from executable, writable data from executable data, so that you can't actually execute even if you jump to your own code. And also, there are some compiler compiler flags in recent times, such as Fortify Source and Stack Protector, which try to protect against buffer overflows. And if there are any package maintainers over here, please fortify all your packages, because it really helps. But yeah, so this is still not enough. The address space random layout randomization is often not random enough to not to be brute forced, and heap overflows, which is another type of memory corruption. It's very difficult to protect against those. And the NX bit can be can be circumvented by, instead of jumping to your own code, jumping to useful code inside the original program itself. So you instead of so you insert pointers to useful code in the application itself, and then use the code of the original application against itself. But the situation is even worse, because not so all these protection mechanisms need to be enabled at compile time, and there is a lot of old code out there, and there are also even new packages sometimes don't apply these mechanisms. And there are also still some flaws in how the mechanisms are implemented on some systems. So the question arises: can we do more? So if we see that data execution prevention prevents your untrusted code from being run as untrusted data from being run as code, we might say, and the counter attack is that we, instead of injecting code, we inject pointers to trusted code, untrusted pointers to trusted code. We might say, can we prevent pointers to code being used as jump addresses? So the answer is that we can do this through a technique called taint analysis. And in taint analysis, we track what code is trusted or untrusted, and then whenever data gets copied, you also copied the data of whether it's trusted or not. And if you combine two pieces of information, for example, when you add two integers, you can, or the trust information, so that the least trusted piece of information decides whether it's trusted or not. And when you actually try to when the code actually try to jump to an untrusted pointer, a check is done and an error is raised, and yeah, so you can corrupt anything you like, but when you try to use it, it will blow up in your face. And these systems already existed, but they're slow as hell. Yeah, so often in order of magnitude, because you have to do all the copying and maintaining whether it's trusted or not. So we tried to see whether we could make it faster. So we used, in Minemu, we used two tricks to try to make the propagation of taint faster. First, we have a novel memory layout. So this is how you can view the Linux kernel memory layout on 32-bit. So you have the high quarter of the address space is in use by the kernel. If you read or write from it, it will generate a fault, and then the rest is used by the user process. So we changed this layout a bit. So we have two equally sized areas of memory, which and one of the pieces is in use, can be used by the user process, and the other one is used to hold the taint information. And then there's a third piece which is used by the emulator itself for JIT translation code, because everything is translated. So during execution, only the user and the taint pieces of memory can be accessed by the program, and because they are of equal size, we can, if we want to propagate a write to an address in the original memory, we can just add a number, and there we have the address of where the trust value of this address is in taint memory. And because the way the memory is laid out, if the process tries to write into the taint memory, or it will generate a fault, so we will detect it at least. So if we want to access the taint memory, we only have to add a constant. So the nice thing is that on Intel, you can add a constant to any addressing mode in the machine code instructions, and have another addressing mode which accesses the same memory location, but with an offset of a certain constant. So, for example, for an instruction which accesses the memory at the EDX register, which is we can have an addressing mode which accesses EDX plus some constant, and that holds for all, even the all memory addressing modes, even the more exotic ones. So the second innovation is that we use SSE registers. So we emulate a processor without SSE registers, and then we hold these addresses as we use these addresses to keep the taint value for the general purpose registers um, so that we don't have to store them in memory, so it's much faster. So this is how it's done. We use 2 SSE registers to hold the taint, and so we separate them in 4 columns, and yeah, so we can store the taint for all 8 registers. So if we want to, for example, add the taint from a memory location X to the EDX register, we can do that very simply. We just identify the column where it's in, and then through the SSE instructions, which are quite powerful, we can first load the taint from register, the taint from memory at location X plus the constant into memory, and then do an OR, and then yeah, we have in just 2 instructions we have done the propagation for this instruction, and most instructions will need 1 or 2 extra instructions to propagate taint. So we tested the effectiveness of this method, so against a lot of exploits, and in all of them they yeah, the exploits were caught. And it's important to know that the vulnerabilities that are caught don't have to be known beforehand. So if there's an unknown vulnerability, you can catch it with this tool. We also did performance tests. So for IO-bound applications, the performance is quite reasonable because there's not a lot of number crunching. So most of the time it's just copying data, and for that the overhead isn't that much. If you want to do number crunching, such as encryption, the overhead seems to be almost 3 times as slow, but it might still be useful for some applications. Your server might not be loaded at all, and you really want your data to be secure, and so it's you have to make a trade-off. We also tested it to very IO bound, very CPU bound, so very difficult for this system applications, and overall it's 2.4 times as slow, and we tested it against also some real-time, real-life applications. There are some limitations to this system. We don't prevent memory corruption. We only prevent when it's used. So that's the best we can do with this technology, but it's still quite useful, I think. And there are also some corner cases where if you can, before you can execute your own code, can find some a pointer, you can write something to arbitrary memory, and that something is trusted, then you also have a problem. But this is just a very small subset of vulnerabilities that are discovered. So and there's also a limitation if you don't overwrite a function pointer, but just something else. For example, does this user have the right to read this file? Then you also are, it's also not caught, because it's not caught because you never check for whether a function pointer is trusted. So in some cases we can also catch other vulnerabilities if we add hooks to certain functions. For example, to a MySQL query, we can have detailed information about which data in the MySQL query is, or in the SQL query is trusted or not. So, so we could have more information about SQL injections this way, because you can, if you find an AND or SQL keyword which is untrusted, then it's wrong. So if there's, I don't think there's time, but yeah, so you can, the source is available at the website. Yeah, we don't have time for questions, but if anyone has questions.